Hi, everyone, and welcome back to the Regression and Beyond series. So, previously, I did a video talking about kind of like longitudinal situations where you might use a latent growth curve model or a multi level model. I then followed that up with a quick video on the basics of structural equation modeling, so getting a little bit more into latent variables. And in this video, I wanted to get in a little bit more into multi-level models, or also more broadly, you can call them linear mixed effect models. So as before, you can find the script file and the data that I'm going to be running through for this video linked below. Just running through the usual. Going to import the data. And in this case, again, keeping things quite simple, but naturally things can get quite complex with these types of models, but we're going to try to keep things relatively straightforward, at least in this video. So in this circumstance, we have an ID variable, a dependent variable y, and an independent variable x. X and y, approximately normally distributed continuous variables, and then we have the ID. So again, just a hypothetical context, but I kind of have this set up as if it were, if you did something like a survey of 50 states and had a random sample of 100 people in each state. That could be a case where you might do a multi-level model or a linear mixed effect model. Because we want to see how this, potentially, for example, how this thing at an individual level relates to this other thing at an individual level, but we also want to take into account, for example, that maybe people in the same state are going to be more similar to each other on maybe a certain set of views. Again, just a hypothetical context. So one of the common first steps when you're going to do a multi-level model or linear mixed effect model is centering variables. Now, we've done this before, and the reasoning again is basically the same. It makes it so that we can interpret things a little bit easier. Specifically here, it's usually about having a straightforward interpretation of the intercept. And there's different ways that you can center. Here, we're going to do what's called grand mean centering, but you can do different things, like you can do group mean centering and things like that. Again, keeping it relatively straightforward. Here, the grand mean centering. So we're just going to turn everything into a deviation from the mean, and then the mean becomes 0. So I just created that new variable here. I'm just calling it xc, so the centered version of the independent variable. Not super critical here in this example that we're going to running through today, but just running through that step so you can see it, because you'll probably be doing the grand mean centering or some sort of centering. So at the start, just to give an example, we're going to be doing multi-level models, but let's start as if we were just going to do like a classic linear regression, ordinary least squares estimation, regressing y onto our centered x variable. And we get an estimate of about 0.46 for the coefficient, 0.01 for the standard error. Not going to focus too much on that, but we'll kind of keep that in the back of our minds so we can compare when we get into the other models. So another common thing to do is to look at the ICC, interclass correlation. So this is a package you can use to that, kind of several different packages you could use to get ICCs. Here in this case, the method I'm using here in the package, we want this ICC1, and specifically we want to know about our dependent variable. And the interpretation here would be how much variation is at level 2. So again, at the if we're using a hypothetical like all 50 states, this would be the variation in the dependent variable at the state level. What proportion is at the state level versus the individual level? So generally speaking, often you're doing a multi-level model because maybe there's a good chunk of the variation is actually at the state level, for example. Now, usually kind of the starting point and often an ending point with a multi-level model is doing a random intercept model. So I'm going to use two different packages to do this. One is Lavon, which I really like. It's really set up largely for kind of latent variable modeling, but you can do some forms of multi-level modeling with it. And I think it's pretty user friendly. So here I'm starting there. You'll see that we're specifying each level. Again, we're pretending it's individuals or states. And here we're just saying, yes, we have these variables measured at the individual level, right? The regression model there. And then here I'm just specifying the variance of the dependent variable at level 2 or at the state level in this hypothetical example. So that is the kind of the quote unquote random part, the random intercept part. Now we run that and we can have a look. So first we get the regression, so the coefficient 0.247, notably smaller than the one we got from the OLS. Standard errors about the same. See that intercept at level 1 is going to be 0 because we're going to have the intercept, the random intercept at level 2. So we have that up here. And then we have our level 1 residual variance and our level 2 residual variance. So that would be a relatively simple random intercept model. Now, it's typically quite common to also estimate the quote unquote kind of robust standard errors using something like some version of a sandwich estimator. So we'll run through that. I'll note one alternative. Some people will do, even if you have clustering, one possible option would be, again, do something like a typical like OLS regression model, but then use like cluster robust standard errors, which is a possibility. But here we're doing everything the multi-level model and what we'd call the cluster robust standard errors. So slightly different versions of robust standard errors that we've done before. So with Lavon makes it quite easy for us to get those. So you'll see basically the standard error just increased a little bit. Now we can look at the ICC again here. Basically the same, though notably it can be a little bit distinct again in your specific situation, because technically there can be a little bit different. This would be the residual ICC. So the amount of unexplained variance that's at the between or a level 2. So it's a little bit weird to think about, but it's kind of the flip side. So rather than the amount of variance at one level, it's the amount of residual variance at level 2. Now, it's quite common to test against what's called a null model, or just what we call the random intercept only. Like we've done before, just testing against an intercept only model. We can do a version of that here, just with a random intercept only model. So that's what we're just setting up here. You're saying we're just going to have intercepts, or the random intercept only. Again, just looking at the ICC, nothing super dramatic, but a little point about that because comparing ICCs can be quite meaningful. But then usually kind of the key part here we want to see is kind of our main model that includes that predictor. Is that better than that intercept only model? So we can do the likelihood ratio test, 1 degree of freedom difference, right, with a predictor versus without a predictor, and then we can see indeed that it is different. So this would broadly support, yes, we have a good random intercept model, basically. Quick thing to show here, probably wouldn't be appropriate in this like hypothetical context that I brought up, but there can be situations where you're going to model things at multiple levels. So again, in the context like Lavon, when you're thinking about multi-levels, you can have like a latent variable that's at level 1 and at level 2. You might have some construct. This context we're talking about, we think about like opinion polls, or we're going to ask people a series of questions, right? And we could have an individual, their responses to those questions, but we could also have like a group of people. So everyone within a state, on average, how are they responding to these set of questions? So again, just kind of showing it that you could do something like this, but you probably wouldn't do exactly this. But just to show you, again, you could have regression at multiple levels. So you see here, this would be, again, theoretically, maybe it doesn't quite make sense, but in principle, this would be the idea of at the individual level versus at, again, this hypothetical context of the state level. And again, we can test models against each other. So although I really like Lavon, one of the limitations, especially as it comes to things like multi-level models, or what we can also call linear mixed models or linear mixed effect models, generally pretty limited in terms of the capability. So one of the really common packages that's used is LME4, LME, linear mixed effect. Hence, we're starting to use that language. But in principle, the math is the same between a multi-level model and linear mixed effect model, though they can mean, different things depending on kind of the context of who's talking about them. But generally speaking, yes, a multi-level model, like the one we ran, a random intercept model, you could also call a linear mixed model. So first, now let's use this package to run what we just did in Lavon, that random intercept model. So obviously the code is going to be a little bit different, but the key part, we have the regression here, and this is the random intercept. Like when we've done random intercepts before, we often denote, or just a intercept only model will denote it with a 1. So that's a similar idea here. And this is our cluster ID. So it's saying random intercept associated with this at the cluster level. I'll note here, or kind of later, I'm setting this so that we use maximum likelihood estimation. And then now we get this output, so it does look a bit different, but the breakdown, the random effects first is what we get. So this would be the random intercept, and this would be the level 1 residual variance, and then we get our coefficient right there, which notably you will, if you remembered the previous estimates, it is different than both the previous estimates that we just had, and different from Lavon. Won't go into a lot of it, but basically it can come down to combination of maximum likelihood estimation and specific procedures for optimization. But main point, I just kind of wanted to bring that up because you generally want to tread carefully and have a really good rationale for kind of exactly what you're implementing in your analytical strategy. In this case, just trying to illustrate the basic steps, but want to make that point. In terms of ICC, just to show you again, you can calculate it yourself. Again, the residual, so we're taking that random intercept and then what we would generally call the level 1 residual in order to calculate that. Now, if we want to get robust standard errors, it takes a little extra work. So again, that's why I tend to like something like the Lavon package, because it makes things really easy for us. Now we're going to get this other package. And now we're going to do the sandwich estimation essentially ourselves to get those cluster, specifically we want those cluster robust standard errors. So I'm not really going to explain all of that, but just to give the background, this is specifically how you would do that to calculate things. So there we go. It took a second, but now it popped up. Again, kind of annoying that we have to do the work ourselves, rather than just having the computer do it in the background. But ultimately, we can get the same goal, and they are generally going to line up with the ones you'd get from Levon as well. Another small kind of irritation, you don't get the p-values automatically, but of course we can calculate them ourselves. So this is just a quick example of how you'd do something like that. And again, I'm using Z, but potentially, you could use a T distribution or whatever the specific case that you want to do. Quick note again with that, if you were going to calculate this, if you were in a situation with a negative z-score, you'd have to do some slight changes. And then I have a little note here about how you can compare things between the Levon output and LME4. But really what I get into next is, of course, we can move beyond random intercepts. We can also add in random slopes. So that's what I want to move to next. We can move into a model with a random intercept and a random slope. Though, things did not go as planned. So in this case, not really going to work out for us, but want to show you this is how you would do that. Rather than having a 1, we now have the independent variable name right here with the ID. So that's going to give us the random intercepts and the random slopes. In this case, yeah, we have what's called a singular model. I'm not going to rant about it too much, but generally it means that something is not okay. And in this specific case, it's basically because that random slope is essentially 0. So that's why we have an issue going on, which could be the case of, maybe you have some maybe theoretical flaws in the background of your model and it's a bit misspecified. But of course not, every random intercept, random slope model is going to be singular. So just want to illustrate that, but also want to make this point. If you're running into singularity type issues, it's good to maybe return to the drawing board because there's maybe something kind of fundamental that maybe you're overlooking about the specification of your model. You can explore more in the help file and look at other things as well. But just to kind of finish off here, noting again, running through those basics, random intercept to random slope, but you can get into all sorts of crazy things with multi-level models and linear mixed effect models. There's, of course, generalized versions, which I'll probably do a video about at some point. So a generalized linear mixed effect model. So for example, if you had like a dichotomous dependent variable, or maybe a count dependent variable, it is possible to do like a multi-level model version of these things. Another quick note, if you are using the LME and you do something like random intercept and random slopes, by default, it's going to include the intercept slope covariance, which you may or may not want, but something to be alerted to. Basically, just check your degrees of freedom can be one of your little indicators of seeing if it's doing that. Again, you might want it, you might not, but just something to be aware of. Also, another note, we did a random intercept and random slope, but it's possible to do a random slope model. So here you'll see we put a 0 now. That's basically saying, hey, no, we don't want the random intercept. But just like we did the random intercept and random slope model, we're including that predictor name in there. So that part's the same, just adding that 0. So we're saying we just want the random slope there. Again, you get the output that roughly looks similar, but now, again, now it's not an intercept, it is the slope. And as I noted before, we set the REML to false, and that meant we were using maximum likelihood estimation. But you could use the restricted version of it. That's what the REML is. General rule tends to be seems to be pretty good with a smaller sample size, but some things to think about, adding to the fun complexity that you have to get into with these types of models. But I hope you found this video helpful, and I hope you have fun exploring more linear mixed effect models.